Welcome to EDU World Space.
The things we know from this problem is that we have a tungsten heating element. It is connected to a battery with a negligible internal resistance. And at a temperature, let's call it Ti, which is equal to 80 degrees C, it draws a power, let's call that Pi, of 480 watts. We can assume that the conditions are such that we can use table 25.2, and we're also told to use equation 25.12 with a reference temperature T0 of 20 degrees Celsius. And we want to know at a temperature, let's call that TF, of 150 degrees Celsius, what is the power that is consumed by this heating element. So since we're told to use equation 25.12, I went ahead and wrote it down, and we're also told that we can use table 25.2. So this alpha over here, that coefficient corresponds to the one for tungsten, which is 0.0045 per degree Celsius. Now, given that we have to find a power, and we know that we have to use an equation with resistance, that leads me to think that I should use this equation here. Power is equal to the potential difference squared over R, right? But R is a function of temperature, so let's write that. So then my power becomes a function of temperature. Now, for each case, before I do that, let's rewrite this as V squared is equal to PR, right? So we have this situation where you supply some potential difference, and then at Pi, at some Ri, at some temperature I, you have Pi. And what I mean by Ri, for example, this means R at temperature I, which is equal to R naught 1 plus alpha Ti minus T naught. Okay, that's what I mean by this subscript I. But we don't know V, but we're given Pi, and we're given the temperature Ti, and we also don't know R0, but we're going to solve this in such a way that we don't need to find R0 or V. But since the potential difference is applied by the battery and it has no internal resistance and so on, the potential difference again is applied in the case where the temperature is different, is the same, right? It's the same battery. Sorry, that should be an F. And what I mean by RF is R at TF, which is equal to R naught 1 plus alpha TF minus T naught. Okay, so since these two voltages are the same, then we can set these two equations equal to each other, or basically substitute from the top equation, substitute for V squared. So I'll take this and plug it into here. So I have P I R I is equal to P F R F. And we know Pi, right? This power that's given at Ti, which is 80 degrees Celsius, this was given to us. And we want to find PF. So let's rearrange this a little bit. So PF is equal to RI over RF times PI. Okay. And now we can right, substitute for Ri and RF from these two equations above. So we have, let's write on the next line, PF is equal to R naught 1 plus this alpha for tungsten, and then our TI was 80 degrees Celsius minus 20 degrees Celsius. That's the T0 that was given to us, divided by R0, 1 plus 0.0045 times 150 degrees C minus, again, the reference temperature, times 480 watts. Make sure I got the numbers correct. Indeed. Okay, and notice that we don't even need to know the R0 because they cancel out. And when you compute this, you find that the power consumed is 360.6 watts.